So let's work an example of a streamline here just to drive this home. We'll go back to the example that we were working on before. Remember that our velocity field v was defined by v0 over L times minus x I hat plus y j hat. And so this is our velocity field. And again, that means that the x component of the velocity u is equal to minus v0 x over L. I've just multiplied that through. And the y component of our velocity v is equal to v0y over L. So for any value of x and y, we have a value of u and v that is our velocity field. Well, the streamlines are defined using this relationship here, which says that dy by dx, oops, go back and look at that last note. dy by dx, that was an error in the last video, heyo, is equal to v over u. And so we can put that to use by saying that dy by dx is equal to v0y over L divided by minus v0x over L, simply subbing those in. And you'll see that some things cancel out here, right? The v0s are on top and bottom, they cancel out. The L's are on top and bottom, so those cancel out. And all we're left with is minus y divided by x. And so the equation of our streamline, pardon me, the equation of our streamline is actually governed by this differential equation, dy by dx is equal to minus y over x. And so we can separate and integrate to solve this pretty quickly. So I'm going to divide this side by dy, multiply up by dx, and so I can rearrange this to be dy over, dy over y is equal to minus dx over x. Now all we need to do is integrate both sides, and we'll be able to figure out the equation of our streamlines. And so the integral of 1 over y, well, that's the natural log of y, ln of y. Integral of 1 over x, that's the natural log of x. But remember, we didn't put limits on this, and so we have some constant of integration, c. And so now we can rearrange this a bit and call it the natural log of y, move the x over here, plus the natural log of x is equal to a constant. And if we put those together, remember that's the same as multiplying, and so we can say ln of x, y. Right? If you add natural logs, they become multiplied inside, is equal to the constant. And so if we take the exponent of this to both sides, we can get that x, y is equal to a constant. Be careful here. This constant and this constant are not equal, right? We took it to the exponent. That's all that is. So we can use any letter we like, but constant seems to be nice there. And so for a given streamline, all we do is pick the value of c. For any streamline, pick a value of c. And so it might actually be more convenient as we use this to put this in a form that we can think in terms of. And so we might say that y is equal to c over x. And if you look at that, what this tells you is that the equation of the line looks like 1 over x multiplied by a constant. And so we can graph this kind of thing, right? So let's give ourselves some axes here. Maybe we'll call this one x and this one y. And let's just say I picked a value of c, 2, whatever number it is. For a value of c, I can run over the whole range of x's, and it'll give me a whole range of y's. And you'll remember that 1 over x looks something like this. And if we chose to drop the velocity vectors on top of this, you'd see our velocity field moving along this line like so. But we could pick a different value of c. So let's say this is the streamline associated with a value c1. If I throw some other value of c in there, it's just going to give me a different curve. So maybe this is the streamline associated with c2. c equals, I don't know, 47. Doesn't matter. And once again, it will also be tangent to the velocity field of the particles going through there. And just for giggles, we could do a negative value of c, which is going to give us something like this. So we could call this one C3, and again, it will be tangent to a series of velocity vectors that go down there. And so this is a way to visualize a flow velocity field.